In this video, I want to cover orthogonality of functions and of vectors. Orthogonality is really crucial to why Fourier analysis even works, but I'll be looking at it in two particular cases, the discrete case, and in the discrete case we'll be talking about two vectors, and if you multiply them element by element and then sum up the result, if that result gives 0, they are orthogonal, and we'll see why that is in a moment. In the continuous version of that, we just multiply two functions together, then integrate, and if that gives 0, that means those two functions are orthogonal to each other. With regard to the discrete case, I'll just add on that if we consider orthogonal vectors, a complete set of them within a matrix, that matrix takes on very special properties, which means that we'll be able to invert it just by interchanging rows and columns. We'll get to that midway through this video, but that's a real benefit of orthogonality and why we find it so interesting. Okay, so just a reminder then of the link between functions and vectors. Imagine we had a continuous function f of t shown here. Then we could have a discrete function just composed of sort of digital samples, if you like, where we've just got the value of the function at a number of different locations, in this case in time. And as you know, we could just store those samples in a tall column vector. In this case, where we've just got a mere 15 samples, that would be a 15-dimensional vector. Now, to simplify discussion in this video, I'm going to consider a very, very simple case. Imagine that we just have two sample points, okay? Why am I doing that? Well, it means that our vector now only contains two elements. But the key point is, of course, we could have many more samples, and so much higher dimensional vectors to cover the more realistic case. But I'm using just two values here so that we can actually see easily what's going on. So as I said, that's a vector, and two elements captures just two sample points. So notice we're using a vector to basically represent a discrete function, and more generally other functions would be vectors of higher dimensions. Okay, so orthogonal vectors. So here's a vector A. This is maybe what you're more familiar with for a vector. We've just kind of got, if you like, a kind of direction and magnitude, but what I want to insist on is that a vector is just a list of numbers, and so therefore a vector can represent a discrete function. So if you like, this is a function here in vector form, and this also is another vector, which we know is going to basically represent a discrete function representing a function in general. It's just that here we've only got two sample points for each one. Now, we know, there we go, we've just got two components to vector A, two components to vector B. It just gives the components on the x and y axis for those two vectors. And so we know, hopefully, that we can talk about a scalar product or a dot product or an inner product of two vectors by definition given by this expression here. So A dot B is the magnitude of A times magnitude of B multiplied by the cosine of the angle between them. Now it turns out, you're welcome to go off and check, that is equal to taking AX, multiplying it by BX. So here's AX, the x component of vector A, and there is BX, the x component of vector B. Multiply those two, and then add on the product of the y components. So AY multiplied by by, and that expression is equal to AB cos theta. Now, if that result is not 0, then these vectors are not orthogonal. So here we've got a case where these vectors are not orthogonal, and what I'm going to mean by orthogonal is when that angle theta is at 90 degrees, or indeed I guess 270 as well would also count as orthogonal, but really just think about the case of 90 degrees. Here it's not, so that result will not be 0, and it means those vectors are not orthogonal. However, if we were to rotate A there, so we've got new components AX, AY, Now it's easy to see that angle theta now, I'm representing it by that square there, it's now a right angle, 90 degrees or pi over 2 in radians. These are now orthogonal vectors because when you plug in 90 degrees or pi over 2 into the cosine, that is now equal to 0, and so whatever the magnitude of those two vectors is, it's multiplied by 0, so that outcome is 0, and that by definition means they are orthogonal, and here geometrically you can see why that is the case. But what we want to do is generalize this concept to higher dimensional vectors, which in turn generalizes to discrete functions which have many more components, which in turn, as we'll see presently, generalizes also to continuous functions as well. So remember that definition there. Well, in general then, for any number of dimensions, here I'm showing for capital I dimensions, it's just the summation of the element by element product. So you just do basically this, but you carry on the element by element multiplication for all of the elements in according to the size of the vectors. And then once you've done that product, you just sum them up. And that is going to give you the dot product or the scalar product. Okay, so let's look at some practical examples. Imagine we've got a discrete function. Again, I'm only considering 2 sample points for brevity here. So there's one discrete function, there's another discrete function. So this one would be represented, imagine that's height 7 there, so 7, 0, a value of 0 there. And this one, imagine it's 0 here, and a value of 8 there. So there's vector f1 for that discrete function, vector f2 for that discrete function. This one is 0 and a height of 8. What we do then to do a scalar product or a dot product is we multiply them point by point. And as you can see here, this times 0 is 0, this times that is 0. So the output, the kind of function there that's the product is just 0, 0. Now to do the scalar product, we need to sum up that vector, sum the elements, and we see that it gives 0, which means those two discrete functions, by definition, are orthogonal to each other. Okay, let's look at a very similar case now of 2 delta functions. Here we've got a discrete delta located at position time t is equal to 1. And then we've got a discrete function f2, where this is now a delta function located at time t equals plus 2. Okay, so there's a vector for the first delta, a vector for the second delta. We do point by point multiplication. We get a 0 and a 0 because it's 1 times 0 gives 0, 0 times 1 gives 0. So therefore the output vector is 0, 0. If we sum that up, it gives 0, which means those two delta functions are orthogonal to each other. And in fact, any delta functions at different positions to each other on much higher, in much higher number of samples per discrete function will also be orthogonal to each other. It's only when they're at the same position that the product would give a 1, and when you sum will give a 1, and so that means they're not orthogonal. Okay, so let's look at a more interesting case now. Let's consider a sampled cosine function for the discrete function 1. And so imagine that as cos 0, which is just a flat value of 1 for every single possible moment in time. That would be the definition of cos 0. It's just that we're only looking at 2 sample points, so it's 1, 1. Let's look at cos t. So that's just a particular unit frequency. And so here, just to help you show the frequency that I'm using here, I've defined it such that the cosine is equal to 1 at that sample point. And you can see the function comes down, and then it's minus 1 at this point. So obviously I'd need to manipulate the frequency in there so that that happens. But you can see the point. I've just sampled a cosine function here. And then it would go back up, and then we'd be periodically repeating that. But we're just considering 2 sample points. So cos of 0 for the first function, cos of t, or some multiplication in front of the t, is just a cosine function for f of 2. And so this one is a 1, 1. It's just 1, 1. This one is 1 minus 1. That's vector f2. If we do point by point multiplication, so we get 1 times 1 is 1. 1 times minus 1 is minus 1. So therefore, our product of the 2 vectors, if you like element by element product, is 1 minus 1. Then to do the scalar product of those 2, once we've done the product element by element, we then sum it up, And we see here 1 plus minus 1 is 0, which means that cosine, that discrete function, is orthogonal to this cosine of that particular frequency. So this f1 and f2 are orthogonal to each other. And in general, cosines of different frequencies are orthogonal to each other. It's only when their frequencies match that they would not be orthogonal. So an example I could have shown here would have been cos 0 times cos 0, and that would be 1, 1. Sum that up, you get a value of 2. Cos 0 is not orthogonal with itself. Or if I had done cos t times cos t, I would have 1 times 1 is 1, minus 1 times minus 1 is 1. Sum that up, I get a value of 2, which means cos t is not orthogonal with itself. Okay, so that all may be well and good, but you think, well, what is the utility of that? Well, perhaps I can give you some insight here. Imagine then we're expressing some discrete function by a vector x, and we're saying it consists of basis vectors contained in a matrix B. Think of the columns of B. You could think of them as delta functions, or you could think of them, discrete deltas, or you could think of them as discretized sine and cosine functions. Just bear with me for the particular definition at the moment. What I want you to think about, though, is the columns of B containing a complete set of orthogonal functions as basis vectors. And what we're saying here is that we're going to synthesize or create a vector x, which represents a discrete function, by adding together the columns of a basis vector matrix B. And C is a vector of coefficients that tells us how much of each basis vector to use to add together to create or synthesize a particular function x. Fine, I mean, we've kind of seen this with the delta function. Hopefully now you're beginning to understand this a bit more in the context of using sinusoidal basis vectors or basis functions for the continuous case. And so what we'd be doing is saying, well, okay, this is all very well and good. If we're given coefficients C, then we plug them into this matrix vector expression, and it synthesizes a vector x. Fine. But what if we had a function x and we wanted to find the coefficients? In other words, we want to analyze that vector x and find the coefficients for a particular set of basis vectors that would be able to be used with this to recreate the function. So if you like, this is like a synthesis, and this is like an analysis. What are the coefficients of the basis vectors, whether it be deltas, whether it be sinusoids, whatever your choice of basis. Well, normally, you can see just by very simple manipulation, if x is equal to bc, then to find the coefficients of b that would give us x, then we'd have to face doing an inverse, okay? So what I'm saying here is, if you like, I've just put b down here, and so that's 1 over b, which is b minus 1. So the inverse of b would need to operate on my discrete function x to give me the coefficients for the basis vectors that are in B. Now, finding inverses of matrices is not trivial, okay? But this is where orthogonality comes to the rescue. If we have orthogonal functions in B, then the beauty of it all is, wow, look how simple this is. We can do the inverse just by swapping the rows and columns of the original matrix B. And this is true for what's known as an orthogonal matrix, or a unitary matrix if we deal with complex values. But look at the simplicity of that. And so this is a great motivator for using orthogonal sets of basis vectors. So that's like a kind of an aside to give you a bit more insight into why this concept is so useful. And we are implicitly making use of this when we do Fourier analysis. That's why Fourier transforms and inverse Fourier transforms are so simple to do because of this relationship. Okay, so getting on to functions now, and very simply and crudely, you could think of a function as like a vector that approaches infinite dimensions. Okay, just imagine tightly packed samples going from minus infinity to plus infinity. Obviously, in the real world, we can't really face the minus to plus infinity, but you can get closer and closer as an approximation to a continuous function just by taking lots and lots of samples, very finely spaced, if you're able to do that. Anyway. Nonetheless, let's deal with continuous functions in the strict sense. And this whole notion of orthogonality that I've been talking about applies for continuous functions as well. So we're saying take a function f1, multiply it, if you like, value by value by value. Obviously it's continuous, so there are infinitely many values within some period of this function. Here I'm assuming these are periodic functions, but this would still apply if t is going out to minus infinity and plus t is corresponding to plus infinity, this would still hold, but I'm just doing a limited range here. So you just do kind of value by value product between a function f1 and function f2. If you do that value by value multiplication, take function f1, function f2, multiply them, and to get a new function, and then if you integrate that product, if it's 0, then we say those functions are orthogonal. Okay? Right, so for Fourier analysis, this holds. If this is a sine and this is a cosine, effectively that always holds. A sine and a cosine are orthogonal to each other, whatever their frequency. However, if f1 and f2 are both cosines, then it only holds if the frequencies are different. Or if they're both sines, then this only holds, again, if their frequencies are different. If their frequencies match, this is not true and they're not orthogonal to each other. And in fact, that non-orthogonality is crucial for why the Fourier transform works, or why the Fourier analysis equations work when we're finding coefficients for the Fourier series, for example. So here is an example of it. Continuous function f1 is just a cosine of frequency 1. Function f2, a cosine of frequency 2. This is frequency 1, frequency 2. Okay, so cosines are different frequencies. Multiply the functions, if you like, element by element, just scanning all the way across here, just taking that times that to get this, and then we come here, that times this to get this, and so on. Just work all the way down. So obviously here and here, here and here and here and here, we should get zeros. So we get 1, 2, 3, 4, 5, 6 zeros, and that corresponds to 1, 0, 2, 0, 3, 4, 5, 6 zeros. So you see, you can work it through, but this is the shape of the function that you get when you multiply this function by this function. Okay. Now we need to do our orthogonality check. This is all part of the process. The sum of this, you can see the plus there corresponds to the minus area there. The minus area there corresponds to the plus area there. Minus, plus, plus, minus. So if you do the definite integral of that, all the pluses directly match and compensate for all the negatives. The net result on integration is 0. Therefore, that function is orthogonal to that function. So more examples of orthogonality, as I've said, sine with every cosine with every cosine of a different frequency, and correspondingly also for sine. And the reason when they're not orthogonal is when the frequency matches, then you get sine times sine of the same frequency, which is sine squared, which is a strictly positive function. When you get the product, sine squared is strictly positive. Integrate that, you're going to get a finite result, so it's not orthogonal with itself. Delta functions, whenever they're at different positions, they're orthogonal to each other. When they're perfectly aligned, they're not orthogonal. Complex exponentials, it's just sort of heads up of where we're going, because we'll need those with the complex Fourier series and the standard definition of the Fourier transform. We can see that with complex exponentials, they are also orthogonal to each other, except this time it's a little bit more subtle. If you multiply this complex exponential, point by point if you like, or along the continuous line x, with this complex exponential, e to the minus ix, then if you multiply that by that, we can see that when you multiply these two exponentials, you just add the argument of the exponential. So ix minus ix gives 0. So that means we're left with exponential 0, which is equal to 1. And that's 1 everywhere. If you integrate that, certainly doesn't equal 0, which means these two are not orthogonal to each other. Okay, but you'll get to that when we look more closely at complex Fourier series and the standard Fourier transform. So in review, I hope you're convinced orthogonality is really a very simple concept, and it's extremely useful for Fourier analysis and for decomposing into orthogonal basis functions and basis vectors. Anyway, the recipe, if you like, is you multiply two functions together or two vectors together, point by point, sum it up and look at the result. If the result is 0, they're orthogonal. If the result is not 0, then they're not orthogonal. Okay, and obviously a single functional vector in general, obviously you could pick special cases like the zero function or the zero vector, multiply that by itself and it's going to be orthogonal, but that's a trivial result. But in general, for meaningful functions, a more general functional vector is not going to be orthogonal with itself. And as mentioned, this is pivotal to why Fourier analysis works. So thank you for listening.